Yes.
Achha. So what we were doing this thing, like the comparison of the hydrolysis of chlorine related compounds. So the thing was that if you've got a chlorine related compound like chlorobenzene, you got no hydrolysis. Why? Because there's already a lot of electrons. So the nucleophile, which is OH-1 or water molecules, their lone pairs are not even going to come close to this because there are already too many electrons there, and the negative charge would repel the negative charge over here. First thing. Then you had halogenoalkanes. So that was mostly AS stuff. That you've got halogenoalkanes. So when you have halogenoalkanes, you got you need NaOH aqueous and reflux. So you do get a substitution reaction. There is hydrolysis. Primary halogenoalkanes, they've got SN2 mechanisms, which is that that the carbon really has a very strong positive charge, this carbon over here. So why? Because it's not surrounded by a lot of groups around it in a primary halogenoalkane. So it's very hard for the Cl to leave because the positive charge is so strong that the Cl is very strongly attracted to it. So the OH-1 comes in and then it knocks out the Cl. But in a tertiary halogenoalkane, so why is the carbocation not formed? Because the carbon has such a large positive charge because it's not surrounded by large groups that the Cl negative will not be able to leave. So which is why the carbocation is not formed. But in a tertiary halogenoalkanes, a carbocation is formed. Why? Because it's very easy for the Cl to leave because this positive carbon is not very positive. Why? Because it's got all these large groups with electrons, 9 electrons over here, 9 electrons over here, 9 electrons on this side. So it's surrounded by electrons on all sides. So the positive charge kind of gets neutralized. So if the Cl takes away the electrons, the positive charge that is on the carbon is not very strong. So it's not going to pull the Cl back. And so the OH-1 can easily come in and join the positive carbocation in the next step. So the Cl leaving is not an issue. So the carbocation intermediate is stable. The carbocation has there's more electron donating alkyl chains around it, and which is why the positive charge density is lower. So we did all of that, and we talked about, and we also talked about this thing that we talked about chirality. Okay, this is something that we did yesterday, and then we started talking about. So we started talking about nucleophilic addition-elimination. Now, this particular reaction was with acyl chlorides. Now, that's an acyl chloride. So acyl chloride is serial bond O with the Cl. So it's a very positive carbon atom. It's got a vigorous reaction with water. No special conditions are required. It even reacts with cold water. So the reaction is like really fast. So C in our COCl group has a strong positive charge density as it is bonded to 2 electronegative elements, which are highly electronegative. So there's strong attraction from lone pairs so there's a strong attraction, and this must be water, I think. So this probably is water. So the water lone pairs are going to be attracted to the carbon positive very strongly. So which is why you get a vigorous reaction. And after this, I think we had changed or switched boards. Just a second, let me. So let me see if we can find the boards. So we started doing amino acids. Not sure which board is this one. So this thing over here, just a second. So we did the comparison of bases, nitrogen compounds. We started doing nitrogen compounds after that. Okay, that thing is done over here. So we'll come back to this. Well, we had also done amino acids. So I'll revise that. So I think I'll finish this over here. So where's the... So the mechanism, where's the mechanism of this thing? Just a second. So we're gonna do the mechanism of this reaction. So what happens in this reaction, I'm going to do it here. The mechanism of this reaction is very important. No idea what this is. Just leave that. So the mechanism of this particular reaction, you've got RC, and it's got a double bond O and Cl. The first thing that happens is that the water molecules are very strongly attracted to this carbon, which is positively charged. So you got these lone pairs over here. And this carbon has a really strong positive charge. You got this oxygen, which has a slight negative charge. You got this Cl, which has a slight negative charge as well. So remember, it's a vigorous reaction. This chlorine-related compound has a vigorous reaction. The lone pairs on oxygen get very strongly attracted to this carbon, which is positively charged. And the double bonded electrons over here, they get repelled by that. The oxygen double bond gets repelled. So the oxygen at the bottom, it brings its electrons and bonds with this carbon atom, and the double bond electrons, they get repelled. That's the first step. So the next step is you got a Cl which is still slightly negative. The water molecule bonds at the bottom, but it loses its lone pairs, which is why it's got a positive charge now. Why? Because its lone pairs got attracted to this carbon atom, so the water molecule at the bottom has a positive charge. The oxygen at the top now has a negative charge. Why? Because all the electrons got pushed upwards. So that's your intermediate that's formed. The next step is that the lone pairs on oxygen over here, they come back. And the electrons in this bond over here, they are, because of those electrons coming back, the electrons over here, they get repelled. So what you get is this molecule. The double bond forms back again. You still have a water molecule at the bottom, which has a lone pair that's missing, which is why it's got a positive charge. And the Cl minus one has now broken away. So the Cl minus one is gone and it has broken away. Now the next very last step is that I'm left with this molecule over here. The very last step is that let's extend this H a little bit. So the very not this. So you had this H. So the H over here loses its electrons. The Cl-1 comes back. And what it does is it tries to, the H gives its electrons back. And this positive H over here gets attracted to Cl. So what now happens is, finally what's going to happen is you've got an R-C double bond O. And at the bottom, you've got an OH now. And the OH, so that's a carboxylic acid. The O gets its lone pairs back, both of them. And HCl gas is formed. So you start seeing misty fumes of HCl. So this is all that's happening. So I'm just going to quickly go through this once more. So first thing, you got a water molecule and its lone pairs are getting very strongly attracted to this positive carbon atom because it's a very positive carbon atom. It's bonded to two electronegative elements. So the lone pairs are very strongly attracted to it. And when the lone pair reaches this carbon atom, the electrons over here, they get repelled and they settle at the bottom, which forms a negative charge at the top. Those electrons come back. When those electrons come back, the electrons over here, they get repelled. So the Cl eventually leaves with its electrons, leaving behind this thing. So the Cl goes away and the double bond is reformed. The oxygen double bond is back. And then you have the Cl electrons -1 coming back because the oxygen over here is electron deficient. So it takes away electrons from the H and the positive H gets attracted to the Cl-1 to form HCl. You clear? Is this mechanism clear?
Yes, sir.
Sir, what is the name of this mechanism?
This is nucleophilic addition-elimination. So you've got things getting added and things getting eliminated as well. So, I mean, the first thing is addition is happening, it's nucleophilic addition. So the water molecule comes in, joins with that. So that's addition. And then things start getting eliminated. Like the Cl gets knocked out and the H eventually gets knocked out as well. Is that clear?
Yes, sir.
Okay, so the first part is everything gets added. And then elimination starts happening after this. The electrons come back, the Cl gets knocked out. The Cl-1, when it gets knocked out, there's still positive charge on the water molecule because it has lost its lone pairs. So it gets its lone pairs back from H, and the positive H goes and bonds with the Cl-1. So the H gets eliminated. So basically an HCl molecule gets eliminated. So what you can state is that water as a nucleophile gets added. I mean, we can. So water as a nucleophile gets added. And HCl gets eliminated. But you check the spelling of eliminated, that's, I think it's an I. So it gets eliminated. So which is why you should, so this is one mechanism that you should remember this is important. So that's nucleophilic addition elimination. So that's all about hydrolysis, comparison of hydrolysis. That whenever, I'm just going to sort of rename this. So it's a comparison of hydrolysis. So remember 3 chlorine-related compounds. You've got chlorobenzene, you've got normal halogenoalkanes, and you've got this acyl chloride. And the hydrolysis reaction. The first one has no reaction with whatsoever. The second one, the carbon is not that positive. So it does have a reaction, but with NaOH aqueous, and you would have to heat it as well. The last one, it's going to have a vigorous reaction. And so every time the positive charge density continuously increases. TK, is this clear? You're going to get questions on this, TK. So moving on. After this, we started discussing that was the comparison of hydrolysis. And after this, we started discussing nitrogen compounds and their comparison as bases. So this is something that we did. So what's a base? It accepts H+1 ions. Why are nitrogen compounds basic? Because they've got these lone pairs, and these lone pairs, they attract H+1 ions. So they attract H+1 ions, which is why they're all basic. The first one is not basic at all, and the last one is very basic. You've got amides. I mean, this one is an amide. This one is phenylamine. I think I should write the names as well. So this one over here is an amide. This other one over here, that's phenylamine. So it's an amine with benzene. This one over here is obviously ammonia. This one is an alkylamine. So I've got these four compounds. I mean, ammonia is just as a reference point. So why is the first one not basic? The reason the first one is not basic is because it's next to a very electronegative atom, which pulls the electrons away from nitrogen. So nitrogen doesn't have lone pairs over here because these lone pairs, they mix with serial bond O. So oxygen serial bond O is very electronegative. Lone pair on N overlaps with the pi electron cloud in serial bond O and is not available. So it's not going to attract H+1. Is that clear? Yes or no? Is this clear?
Sir.
Yes.
What about this one? Same thing happening. The lone pair on N kind of starts to overlap with benzene's pi electron cloud. So but remember, the overlapping is not as much as this one, because over here you had a highly electronegative element. Now the overlapping is just very slight. So the lone pair overlaps with benzene pi electron cloud and its charge density decreases. So it is still there, but the negative charge over here is lesser. So it will attract H+1, but not that strongly. So there's going to be less attraction for H+1 ions. अब ये आखिरी वाले के साथ क्या issue है? When you have a carbon chain, what it does is it does the opposite. It has an electron donating effect. So the lone pair negative charge density is really, really high. So the alkyl chain has electron donating effect. The charge density on the lone pair increases a lot. So there's more attraction for H+1 ions. Remember all of this. Remember the explanation why this one is basic and this one is not basic. Is this clear?
Yes, sir.
Yes.
Just a second. अच्छा फिर ये कि formation of amides. So I've got now these are all reactions that you have to remember. You've got formation of amides. One is nucleophilic substitution of halogenoalkanes, which you've already done. in AS. Like the halogen gets substituted by ethanolic NH3 or NH3 gas. So the Cl gets replaced by NH2, you get an amine, that's it. Or you can reduce nitriles. You can take a nitrile, C triple bond N, reduce it with NaBH4, LiLH4, or you can also add, or you can also do hydrogenation. So hydrogenation can also be done, and the triple bond will go away, and hydrogens are going to get added to it. Then there's reduction of amides as well. Like if you got an amide is NH with a C double bond O. So you can reduce it and the O will go away. So you'll just have a carbon chain with NH. So it's an amine. And another one is reduction of nitrobenzene. You've got a nitrobenzene, you add 10 plus concentrated HCl and you get phenylamine. That's it. So there are 4 different ways of producing amines. And we did this thing. We did diazonium salts or azodyes, which was that azodyes are paint stuff, they're dye stuff. Most of the dyes, clothing, etc., car paints, etc., they need to be very stable. They should not change. When you paint a door, you expect, if you paint it in red color, you expect it to remain red for a very long time. So that means they have to be really, really stable. Paints, I mean, most people don't give a lot of thought to paints, but paint is something that has to be extremely stable. Because, I mean, it would be pointless if the paint just fades away or changes very quickly. So you don't want it to react with anything. I mean, it has to have a lot of inert properties. So how do you make paints? You make it with azodyes. How do you make azodyes? The first thing is you take a phenylamine, you react it with NaO2 plus HCl at a temperature below 10 degrees centigrade, and it turns into a diazonium ion, which is very unstable. This unstable diazonium ion is an electrophile. So what you do is, and it's very unstable, if the temperature goes above 10, it will vigorously react with water to form a phenol. So it will decompose very quickly. So you have to have a very cold environment for this. What you do with this diazonium ion is that it's an electrophile. So you present an activated benzene to it. So the positive ion is going to be strongly attracted to the electrons in this other benzene. And it's going to go and bond with it, forming this azo group. This is your azodye. So it's got to be an activated benzene. The activated benzene could either be a phenol or a phenylamine. Because remember, these two have lone pairs. So the lone pairs are going to mix with the benzene electron cloud. So the negative charge would be a lot greater. So the diazonium ion is going to be a lot more interested in a negative charge that's a lot greater. Okay? Is this clear?
Yes, sir.
Yeah.
So that's so these are azodyes, which are really, really stable. They can come in all sorts of shapes, but the basic, I mean, this is the basic structure, just the very basic structure. You've got a diazonium ion, there could be other groups that could be attached to it. There could be other groups that could be attached to this one as well. But like an example over here. So, but the basic idea is you need a diazonium ion. You can have any groups that could be attached to it, any groups that could be attached over here. So lots of azodye, but the basic idea is the same. Just a second. So here you go. Remember these alternating double bonds, that's benzene. So again, you got an activated benzene ring, so that's a phenol, an OH. This other one is not activated, so one of them is going to be activated, the other one is probably not going to be activated. So here's another one. So one of them is activated, it's got OH. So this one must have been the diazonium ion, which got attracted to this benzene. So all these azidides, all sorts of azidides, you can see where's the N double bond end over here? I think that's probably not an azodide, just a second. So that's an azodide. This one is the activated benzene because it's got an N lone pairs. So all of these are azodides, and these are some examples of actual azodides and their colors. So which one? Just a second. Need not this. This is something else. So I just gave you examples, and we did this one. So just remember all of this nitrogen compounds. TK, I'm going to share the board link. About nitrogen compounds. We'll just go over proteins in the next class, and then we'll try and do past paper questions related to organic. TK. So not really feeling well today, so we'll continue tomorrow then. TK.
Okay, sir. No problem. Inshallah, it'll get better. Hopes.
Okay, take it. Allah Hafiz.